Today, we are stepping into a world that is, well, it's essentially invisible to 99% of the population, yet it's absolutely critical to how our modern world functions.
Right.
We aren't talking about the internet infrastructure or the power grid. We are talking about something a little messier, a little more hidden, but arguably just as vital. We're talking about industrial wastewater.
It's the ultimate out of sight, out of mind infrastructure, isn't it? You turn on the tap, the water is there, you buy a product, it's clean.
Mm,
But when you actually peel back the layers of how things are made, whether it's, the food on your plate, the gas in your car, or the paper in your printer, there's a massive, complex water cycle happening in the background.
exactly. And to guide us through this hidden world, we're doing a deep dive into a comprehensive technical catalog from FRC Systems. They're a brand under the Sulzer umbrella, and they specialize in this stuff.
They really do.
We're going to unpack how they use everything from uh, microscopic bubbles to gravity, and even hired armies of bacteria to turn heavily contaminated industrial effluent into clean water.
And what really stands out in the source material is that FRC isn't just offering one tool. They haven't just built a better filter. They've built an entire ecosystem of machinery.
A whole ecosystem.
Yeah, we're talking screening, separation, dewatering, and biological treatment. It's a complete chain, and honestly, the engineering philosophy here is pretty distinct. It's heavy duty.
So before we get into the nuts and bolts, or I guess the pumps and valves, let's set the stage. What is the mission here? Why do we need this level of complexity? Why can't a factory just, I don't know, put a mesh filter on the end of a pipe and call it a day?
Oh, I wish it were that simple. I really do. Think about what industrial water actually contains. It's not just dirty, like muddy river water. It's a complex soup.
A soup, okay.
It is. It's loaded with fats, oils, and grease,
Right.
what the industry calls FOG. You have suspended solids, dissolved organic matter, proteins, blood, sugars, chemicals.
That sounds incredibly difficult to manage.
It is. If you just flush that into a municipal sewer,
Mm.
you clog up the city's infrastructure instantly. We've all heard of fatbergs, right?
Oh, yeah.
That's what happens. And if you flush it into a river, you cause massive environmental damage. You're killing fish, destroying ecosystems. So the mission here is compliance, obviously. You have to follow the law, but also efficiency, and increasingly, as we'll see, resource recovery.
Right. Turning waste back into value. So the source material outlines a very specific journey the water takes. Let's follow the flow step by step. It starts with what they call the first line of defense.
Screening and oil separation.
Specifically, something called the rotary drum screen.
This is crucial. If you don't get the big chunks out first, everything else downstream, your pumps, your expensive filters, your delicate membranes, is going to fail.
It all gets clogged.
It's like trying to run a marathon with rocks in your shoes.
Right.
Eventually, you're going to stop. And FRC uses what they call an internally fed rotary drum screen.
The internally fed part seems important. The documentation makes a real distinction there. What does that mean for the actual operation?
So imagine a large cylinder made of mesh or wedge wire, and it's lying on its side. In an externally fed screen, water hits the outside. But here, the wastewater flows into a head box and spreads onto the inside surface of this rotating drum.
So the water is briefly trapped inside the cylinder.
Exactly. The liquid falls through the bottom of the drum out of the system.
Uh,
But the solids, vegetable scraps, plastic bits, chicken feathers, whatever's in there, they stay trapped inside.
and then gravity just takes over.
Well, as the drum rotates, the solids tumble. And tumble is the key word here. The drum rotates slowly.
See, I would have thought you'd want to spin it fast, like a centrifuge.
Logically, you would, right? You'd think spin it fast, fling the water out. But in this specific application, speed is the enemy.
Why is that?
If you spin it fast, centrifugal force pins the solids against the screen. They don't move, they just plaster over the holes, and they stay wet because the water can't escape.
I know.
By rotating slowly, the solids tumble over each other. It's a natural dewatering action. So by the time they fall out the other end, they are so much drier.
That makes perfect sense. It's gently rolling the water out of them.
Precisely. Plus, slow rotation means less wear and tear. It lasts longer.
I also noticed a detail in the specs about the cleaning mechanism. It mentioned a spray bar, but with a caveat about water usage.
That's a great catch. So screens get clogged, that's inevitable. It has an automatic spray bar to blast the screen clean, but it's intermittent. It doesn't run constantly.
A huge water saver right off the bat.
Exactly. You don't want to use clean water just to clean the machine that cleans the dirty water if you don't have to.
And these things are beasts. We're talking flows up to 6,500 gallons per minute, with screen openings down to, what, 250 microns?
Yeah, that's 0.010 inches, barely visible. It's the gatekeeper of the whole plant.
Okay, so we filtered out the solids, but let's say you're an oil refinery, or a fracking operation, or even a food processor that fries things. You have free oil mixed in with water. You can't screen oil out, right?
Nope, it just slips right through. For that, you need a different approach. You can't filter it, you have to separate it. And FRC uses the corrugated plate interceptor, or CPI.
Which is the modern version of the old API separators.
Correct, the American Petroleum Institute. The old API separators were basically just massive swimming pools. You let the water sit, and eventually oil floats. But that takes up a huge amount of land.
So how does this CPI work? How does the corrugation, the waviness of the plates help?
It all comes down to Stokes' law. Basically, oil wants to rise, so we want to give it the shortest possible path to a surface. By stacking these plates just inches apart, an oil droplet only has to rise an inch or so to hit the underside of a plate.
It hits the ceiling of the plate above it.
Exactly. And here's the magic. When enough tiny droplets hit that ceiling, they coalesce. They merge into bigger drops.
And bigger drops float faster.
Much faster. They zip up the angle of the plate to the surface to be skimmed off. Meanwhile, the heavy sludge slides down the plates to the bottom.
It's brilliant because it has no moving parts inside the liquid, right?
Aside from the skimmer on top, zero moving parts. Just gravity and geometry.
Okay, so we've screened the chunks, we've separated the free oil. Now we get to what seems to be the absolute heart of the FRC system, the DAF, dissolved air flotation.
The DAF is the workhorse. If the screen is the bouncer at the door, the DF is the security team clearing out the crowd inside. It handles everything that's too small to screen but too light to settle.
And this brings us to the concept of whitewater, which again sounds like we are going rafting, but I assume the physics are different here.
Very different. In this context, whitewater is a stream of recycled water that's supersaturated with air under high pressure. You take some clean water, you pump air into it at, say, 80 to 100 psi.
Yeah.
You're forcing air to dissolve into the liquid.
Like carbonating a soda.
Exactly like that. Then you release that pressurized water back into the main tank, which is at atmospheric pressure. When the pressure drops, the air comes out of the solution explosively.
Creating millions of tiny bubbles.
Microscopic bubbles. The water looks milky white because of them, hence whitewater.
And these bubbles are the engine.
They are. They attach themselves to the suspended solids and the emulsified fats and grease. They act like thousands of tiny life jackets, lifting the contaminants to the surface.
Life jackets for the grease. I love that visual.
It's incredibly effective. Once it forms a floating blanket of sludge on top, a mechanical skimmer just scrapes it off.
Now, one thing FRC highlights here, and it seems like a big deal for the people actually running these plants, is the pump. They use non-proprietary pumps.
Oh, it's a huge selling point.
Why is that?
Imagine it's Saturday night, the plant's at full capacity, and a specialized proprietary pump breaks. If that pump is only made in one factory in Germany, you're down for weeks.
You're losing money every minute.
A lot of money. With a non-proprietary ANSI pump, which FRC uses, you can probably find a replacement part at a local supply house that same day. It's all about operational resilience.
That's a huge practical advantage. Now, looking at the catalog, FRC offers 3 different personalities of DAF systems. First, we have the PCL series.
Right. Think of the PCL as the vertical powerhouse. It's designed for high flow rates, 2,000 plus gallons per minute, but for facilities that don't have a lot of floor space.
The urban factory problem. High output, small room.
Exactly. It uses cross-flow plate packs, like the oil separator, to multiply the surface area inside the tank. It's efficient, compact, and handles high volume.
Okay, next up is the PCCS series. This one looked the most unique to me.
The PCCS is the mobile solution. The entire system is engineered to fit inside a standard 20-foot ISO shipping container.
That is wild. So you can basically truck it to a site, plug it in, and start treating water.
That's the idea. It's plug and play. Think remote oil fields, mining camps, maybe an emergency response where a local plant has failed. You bring the plant to the water.
And finally, the PWL series, the open tank. This one looks like the heavy industrial classic.
The heavy lifter, low profile, rectangular open tank. It's designed for heavy solids loading. We're talking meat packing, poultry rendering.
The really messy stuff.
The stuff that would clog a plate pack in 5 minutes. But the PWL has a really interesting feature, a countercurrent skimmer.
Okay, explain that. Countercurrent means it moves against the flow of the water.
Correct. In most DAFs, The water flows one way, and the skimmer scrapes the sludge the same way toward the exit. But here, the skimmer pushes the sludge upstream, back towards the inlet.
That sounds counterintuitive. Wouldn't that mix the dirt back in?
You'd think so, but for heavy sludge, it's better. By pushing it against the flow, you minimize what's called sludge carryover. It ensures the sludge you're scraping off is thick and stays separated from the clean water exiting the other end.
It keeps the clean water clean. Got it. Now, sometimes physics needs a little chemical help. That brings us to the prep work flocculation.
Right. Before the water even hits the DF, you often need to encourage the tiny particles to clump together. You add coagulants and flocculants to glue them together into flocks.
And FRC has the F-series flocculator. It looks like a big coil of pipe.
It is a pipe coil design, a static mixer, no motor, no blades. The genius here is in the flow dynamics. They emphasize wide radius bends.
Why does the radius of the bend matter?
Flocculation is delicate. You're creating these fragile little clouds of particles. If you put them through a sharp 90-degree turn, the turbulence just shears them apart.
You're destroying the snowflake you just made.
Exactly. The wide bends mix the chemicals gently. It uses the energy of the water flow itself to mix without shearing. And again, zero energy input.
Zero energy is always a winning stat. Okay, so we floated the sludge, we've skimmed it off. Now we have a new problem. A pile of wet sludge. And you pay by the weight to haul that away.
And water is heavy. If you're hauling sludge that is 95% water, you're just paying a trucking company to move water to a landfill. It's a waste of money. This brings us to sludge dewatering.
First is the belt filter press. This feels like the traditional way.
It is the traditional workhorse.
Sure.
Sludge gets sandwiched between two porous belts, squeezed through rollers. It wrings the water out like a sponge.
Is it effective?
Very effective at getting dry cake. But it's messy, and it uses a lot of water. You have to constantly wash those belts with high-pressure sprays or they blind over.
So you're using water to dewater.
Which isn't ideal. And that brings us to the second option. The multi-disc screw press. The source material frames this as the modern upgrade.
This thing is a marvel of engineering.
It really is. It addresses the biggest headache of dewatering, clogging. It uses a screw that rotates inside a chamber made of alternating fixed and moving rings.
And the moving rings are the key.
That's the key. As the screw pushes the sludge forward, the moving rings shift against the fixed rings. The chamber is constantly self-cleaning. It scrubs itself while it works.
So it doesn't get gummed up, even with oily, greasy sludge.
Right, but the aha moment for me, the real insight here, is the water consumption.
I have that stat highlighted right here. Less than 5 gallons per hour per screw.
That is phenomenally low. Compare that to a belt press that might need 40 or 50 gallons per minute. The screw press uses almost no water, uses very little energy, and it's enclosed so there's low odor.
It sounds like for many applications, that's the clear winner. So let's recap. We've handled the solids, the oil, the grease, and we've squished the sludge. But there's one final step. Biological treatment. The final polish.
This is where we deal with what you can't see. Dissolved organics, sugars, proteins, things a mechanical screen can't catch, but bacteria can eat it.
So we are hiring microscopic employees. FRC lists 2 main systems, MBBR and MBR. Let's start with MBBR.
MBBR stands for Moving Bed Biofilm Reactor.
Oh.
You put thousands of these specialized plastic carriers that look like little pasta shapes into the tank. They just float around.
Floating cities for bacteria.
That is a perfect analogy. The bacteria grow on these carriers, protected. The big benefit here is that it's self-regulating. If the biofilm gets too thick, it naturally slows off. It's largely hands-off.
And then we have the MBR membrane bioreactor.
If the MBR is the robust workhorse, the MBR is the high-precision instrument. It combines biology with a physical barrier, a membrane filter.
And these membranes are incredibly fine, right?
Extremely. We're talking pore sizes down to 0.04 microns. That's small enough to filter out bacteria, even some viruses.
So what's the result?
The result is ultra-clear effluent. The MBR replaces the need for a giant clarifier tank. The water quality is so high, it's often suitable for reuse irrigation, cooling towers, wash-down water.
And that leads nicely into our summary. We've looked at the whole chain, from the rotary drum screen taking up potato peels, to the DF lifting grease with bubbles, to the screw press drying sludge, and finally the MBR polishing the water.
It is a comprehensive suite.
Yeah.
And notice the common threads. Stainless steel construction, non-proprietary parts. They are building these things to last in harsh environments. This is industrial survival gear.
But perhaps more importantly, it represents a shift in philosophy. We used to look at industrial effluent as waste to be disposed of and expense.
Exactly. But with technologies like the screw press using minimal water and the MBR allowing for water reuse, we're shifting to resource recovery. The treatment plant stops being a cost center and starts being an asset.
It closes the loop. It's a circular economy in a shipping container.
Precisely. It turns a liability into a resource. And that is where the future of industrial engineering is heading.
So next time you drive past a big industrial facility, a paper mill, a food plant, a refinery, just remember, there's a whole world of bubbles, spinning drums, and floating bacterial cities working silently inside to keep our rivers clean.
It is hidden engineering at its finest.
Thanks for joining us on this deep dive into FRC systems. We'll catch you on the next one.
Goodbye, everyone.